as I mentioned, I'm Anil Agrawal. I'll be teaching you the first part of this course. So there are a couple of courses that I and Dr. Madhavan teach together. Half of the course he teaches and half of the course I teach. So this is one such course, and another one is Advanced Structural Mechanics. Earlier, up until last year, I used to teach first part of both these courses, steel design as well as structural mechanics, but this time we have switched. So I will be teaching in the second part of this semester, but the content is still the same. Okay, so here is an introductory slide for you. Now, what I had shared the lecture notes with you already, right? So again, I would insist that you take out a print and keep that printout with you. And if there is any correction or if there is any comments to be made, you can do that on the printout itself. So here is a small correction. So the slides that I had shared with you were from the previous semester. There is a minor change here on the grading schedule. So it is tentative still because we don't know how the semester will go, how effectively we will be able to accomplish everything. But the idea here is that I will give you a quiz almost in every class, unless there is something exceptional or something. So it will not be a in-classroom quiz. It will be take-home quiz. So I'll give you a quiz. You solve it by the next class and before the next class starts. So we have two classes, one on Monday, another one on Thursday. So if I give you a quiz on Thursday, so I will definitely post the quiz before the class ends, or like before the end of the day on Thursday. So you are required to solve that quiz and upload the answer. And I will explain the instructions of how to upload the answers by next class. Okay, so if the quiz is on Thursday, you are supposed to. So it is. I'm calling it a quiz, but it is more like an assignment. Okay. So that is one way. Another one that is 40%. So that has been given sizable weightage, so that you are always keeping up with what was going on in the course. Okay. Then the second part is the exam, right? So exam will be in the middle of the semester when my part ends. So there will be one exam at that time. I am giving it 30% weightage, and all these percentages can change when we reach that point. So it may, instead of 40, I may make it 50 if I feel like the exam was not very conducted. So basically, I always try to give some benefit to the overall class. And so, for example, if I conducted an exam was 3 hours, but a lot of people were having difficulty connecting with the internet or something, then I may be a bit more considerate and I can reduce the weightage of exam and increase the weightage of the quizzes. Or if suddenly we feel like that quizzes are becoming too burdensome on you and there are too many people complaining about these quizzes, you feel like it's too much of work, then we may reduce the weightage of quizzes, or like whichever way. So if you have any inputs, you can share with me, we can take a poll, we can decide. These things are not hard and fast, these are guidelines, right? And then there will be some assignments. So these assignments will be bigger than quizzes. So quizzes will be usually quizzes. If you have understood the material in the class, it will take you half an hour to 15 minutes to half an hour to solve the quiz and upload the assignment, upload the answers. Assignments will be slightly more elaborate. There will be 2 to 3 assignments, and there will be one project at the end of the course. And together they will be having a weightage of about 30%. So that makes it total 100%. And this 100% is only for my part. I'm not talking about Dr. Mahendra Madhavan. So he will have his own grading scheme. At the end of the course, he and I will sit together. We will add our total scores for each student and then decide on the grading policy. So as you might know, IIT Hyderabad has this letter grading policy: A plus, A minus, then B minus, C minus, and so on. So, and A plus and A have 10 marks out of 10. In the orientation, these things must have been explained to you. I'm just repeating quickly. And then B, then there is A minus for 9, then B for 8, and so on, and B minus for 7, and so on. Okay. So we will we usually go with some kind of a clusterization. We look at around where are the boundaries, very clear boundaries in the scores. So if there are if we spot any boundaries, then we see, okay, so above that boundary, that's where we create the boundary between the letter grades also. Okay, and this is my personal website. This is my email address. Here you can see my email address, right? Right, so you can, it is anil@IITH or anil@ce.IITH, both work fine. And my office is in B block 221. I don't expect you to be able to come to my office, at least in this semester. And this is the last one is actually is more detailed website. So you can find much more information about my research, etc. on this website. The classes, class hours are 2:30 p.m. on Monday and 4 p.m. on Thursday. The link was shared with you. So earlier I used to give a separate link for every class. I find that to be more secure, but now we are Google Meets, Google Classroom allows you to generate a Google Meet link permanently for the class. So that is also okay. But then you will not, if that is the case, then you will not get a reminder before every class that there is a class now. So you have to set your calendar and click on and save that link somewhere, or come to the Google Classroom every day at that time, every Monday and Thursday at that time, and click on that link. So we will see. Anyway, so today I had sent you the link through Google Classroom, but maybe on Monday you will not get any email or anything. You have to monitor, like, you have to check your timetable and click on that link. As I understand, there is one student, international student is also there, right? Are there any international students in this class?
Yes, sir. Kelvin.
Kelvin, right? So where are you now?
I'm in Guyana.
Guyana. So what time is there now?
Well, it's 6:42 p.m. now.
Okay. Yeah, so I'm sorry I'm not mentioning your Guyana specific times. It's only Indian Standard Time. So you may have to do that translation, huh?
Okay, sir. Okay.
So I mean, you are here on time today, but today I had shared the link. But in future, you have to be careful about that.
Okay, sir.
Okay. So, all right. So there are some textbooks. These textbooks are easily available. I think all of them are available on Amazon. These three, the book by Subramaniam and Salman Johnson and Malhas and S.K. Duggal. These are the three textbooks I would be referring to. So this is not, I don't have a specific textbook because there are different materials that I pick from different textbooks. So, but I'm sure all of you guys have some ways to finding the books. Library is not open though, but I'm sure you can find books. So these are not very difficult to find. And then the Indian standard code for steel design is IS 800. And there are many other relevant Indian codes that we will be referring to from time to time. But IS 800 will be the primary code. Okay. So what have you got so far? What are the three things that you need to do for this course to go smoothly? One, you have to print out IS 800. Keep a printed copy of IS 800 with you. Okay. Kelvin, you too, you may not have the copy of IS 800. So you can download it. It's freely available, but you may have to print it. Another one is these lecture notes you can print. That will help you taking the notes quickly. Okay. Or otherwise, if you have two devices, you can use a tablet or something and to take notes there. I'm not insisting on a printout, but have another version of IS 800 with you and another version of lecture notes with you where you can take notes. And the third thing is set a reminder for these classes and keep that link so that you can always click on that link and come to the class. All right, so what is steel used for? Structural steel used for? What kind of structures it is used for? So I mean, we have all seen steel being used for various types of structures, for bridges, different types of buildings. It could be residential building, office building, industrial building. Okay, so these two are pretty much similar kind. Now it is this PEB. So there was a time when these industrial buildings were mostly made with trusses, etc., and columns. But now these are moment resisting frames that are commonly used in industrial buildings, which is commonly known as PEB. Okay, so and then the third primary type of structural system where steel is used is tower or utility poles. So it could be telecom tower, it could be transmission tower. What is a transmission tower? That is used for transmitting electricity. Okay, not transmitting telecom signals. That's not transmission tower. Okay, transmission tower is primarily for electric signal, for electric power. The telecom towers are called telecom towers. Then utility poles. So this could also be the same, meant for various types of transmission lines and so on. Okay, so pretty much everything, almost many of these things can be built with concrete as well, except the industrial building part. So and also some types of towers are possible only in steel. And also when they go with bridges, especially very long span bridges, again they have to rely primarily on steel. So these are some pictures of some of the most beautiful bridges in my opinion. So can somebody tell me the name of the first bridge here?
Howrah Bridge.
Howrah Bridge. If you have the printout, then you already know. Okay, the second one, this one. This is in Sydney. Anybody has watched that movie, Dil Chahta Hai? No? Okay.
Yes, yes.
There was a very nice shoot of this bridge around Opera House. Yes, this is called Sydney Harbour Bridge. Okay. This one is another one in Kolkata. So actually, Kolkata is a big center of steel industry in India, and you can see a lot of big steel structures, steel bridges, etc., still present from very old times in Kolkata, and many big industries which use a lot of steel are also based in Kolkata. So this is Vidyasagar Setu, that is also primarily steels. Cable stayed bridges can be of both kinds. The deck, of course, the slab in all these bridges will of course be concrete, but the beams are all steel, and of course the cables are steel. And so this is Vidyasagar Setu again in Kolkata, and this one everybody knows, right? The fourth one,
Golden Bridge.
Golden Gate Bridge. Yeah, so this was the longest bridge for a very long time, but now I don't think it holds that title anymore. This is in San Francisco, USA, and okay. So both these are from India, and both of these are abroad. So this is in Australia, and this is in USA. Okay, so these are the dates when they were completed. So I showed you some examples of bridges. Now some examples of buildings. Now first one, who can tell me the name of the first building here?
Empire State Building.
Empire State.
Correct. Empire State Building. Good. Second one,
World Trade Towers.
World Trade Center Towers. Yeah. So this is Empire State Building. Where is it? What is the location?
New York.
New York City. Very good. So the World Trade Center Towers, these are also in New York City. They are not there anymore. They were demolished. They collapsed in the terrorist attack. They were also in New York. This is also one of the tallest buildings. Does anybody know its name? Anybody has seen this one or its pictures? This one is in Chicago. It is known as Willis Tower. Earlier it was known as Sears Towers. So when the owner changes, sometimes they want to rename the building. So this is known as Willis Towers. Okay. And then this one?
Petronas Tower, Kuala Lumpur, Malaysia.
Yeah, very good. Petronas Tower in Kuala Lumpur. This one everybody should know. This has very interesting features. Nobody knows. Come on. This is Taipei 101 in Taiwan. Okay. Taipei 101. What is 101 here? 101 stands for something. 101.
Number of floors.
Number of floors. Very good. Yeah. So it has 101 floors. So that's why this is called Taipei 101. It's in Taipei, the capital of Taiwan. Now, the special feature about this building, I'll talk about steel and concrete and those things in a minute. The special feature of this building is that it has a very nice tune mass damper system on the top, because Taiwan is a very earthquake prone country. So this one has something called tuned mass damper, which reduces the earthquake response of the structure, so that a heavy mass is placed on the top of the building. So if the earthquake comes, the building does not vibrate, only that mass vibrates within the building, and it nullifies the earthquake forces in a very in a fancy way. Okay, and this one everybody knows, of course.
Burj Khalifa.
Yeah. So earlier it was known as Burj Dubai, but then it was again the owner changed and the building was renamed as Burj Khalifa. Okay, it is in Dubai. Fine. So can anybody tell me why are these buildings listed here? There is something very common, something very special about these buildings.
Steel structure.
Steel.
They are all steel.
Steel structures.
Yes,
They are iconic structures.
One person at a time.
Iconic
So
structure.
they are iconic structures, but there are many more iconic structures. Yeah. Who else? They are steel. Somebody said. I think that is wrong.
Iconic.
At one point of time, they were all were highest. I mean,
Correct. Who is this? Who is this?
Lohit.
Lohit. Yeah. Good. Yeah, so they were the tallest building at some point of the time. So many of these buildings are not the tallest buildings anymore. Right now, this is the tallest building, but they have all held the title of the tallest building at some point. So Empire State Building from 31 to 72, almost 40 years. World Trade Center for 2 years. Then it was taken over by Willis Tower, which also held the title for quite a long time. Then many these towers in Asia held the title of tallest building. And now, presently, Burj Khalifa has that title. Now, I have coded these buildings. The first 3 are in red and the last 3 are in gray. And this color signifies something. I'm sure you can figure out already, right? So gray stands for concrete. So main structural frames of these 3 buildings are made of concrete. Yeah, main structural frame of these 3 buildings are made of steel. Okay. And you can pretty much see that there is kind of a trend from steel to concrete these days. But this can be a bit misleading also, because you can also appreciate the difference that these 3 buildings were all in the Western Hemisphere, USA, right? And these 3 buildings are all in Asia, right? So also you can say that around 1998 or that point onwards, Asia was growing so much or so fast that the new development came to Asia, and in Asia, concrete is preferred over steel, right? So it does not necessarily mean that steel is being preferred all over the world, but at least in Asia, we can mostly agree that concrete is the material of choice in comparison to steel, and there are various reasons for that. Steel. Can anybody elaborate why is concrete preferred in Asia? Availability of concrete. I mean, in America also there is plenty of concrete.
No, I mean availability of steel.
See, steel is a global commodity, so steel prices are almost the same everywhere, right? So steel prices in India cannot be much more expensive or much higher than steel prices in maybe 10% difference, because otherwise it will be traded very quickly and it will help. Concrete, on the other hand, because it uses a lot of volume, you need a lot of volume of concrete, and the amount of therefore the shipping becomes more expensive. So concrete is not really a globally traded material. Cement could be, but not concrete as such. So
steel is more prefabricated. It is more made in the factory. Concrete is made at the site, and Asians are more labor oriented.
Exactly. So that last part that you mentioned, that in Asia, still the standard of living is relatively low. Our daily or hourly labor charges are low in almost all Asian countries, including Dubai even. So in Dubai, where do they get their workers from? From India and Pakistan, right? Bangladesh. So all these workers are very cheap. They don't have to pay them much, or at least not as much as they have to pay in the US or something. So therefore, any material that is more labor intensive automatically has an advantage in Asia, whereas steel is more mechanized. Production of steel, fabrication of steel, all that requires high skill labor, not so much of low skill labor, which is expensive. So which is more expensive in developing countries and very rare. We don't even get very good quality welders. It's very difficult to get very high quality welders in India or developing countries like India. So for that reason, even now, so for example, when these World Trade Center buildings had collapsed, they had built a new building there, which is taller than the World Trade Center buildings. But it's not the tallest in the world anymore because other buildings have taken over that height. It's called, what is the name of that building? Does anybody know what's the name of that building? Freedom Tower, right? Have you heard of Freedom Tower? Okay, so now they have built a new building. It is already inaugurated and it's functioning. So that building, I think, is slightly taller than these two towers. It's a single building, but that is also made in steel. So, for example, USA still for high-rise buildings, they are still preferring steel over concrete. But just that the center of financial activities has moved towards Asia, and that's why you see more of a concrete being used. And we are quite hopeful because in the last couple of years, I have seen in Hyderabad itself, there is a lot of new steel construction coming up in buildings, bridges, of course. In bridges, when you go beyond a certain span, you have to go with steel. Concrete cannot provide you the solution. But in buildings too, I have been seeing that there is a large amount of development coming in. So, and plus industrial buildings also, steel is the only solution. So there is a good hope for steel in future, okay? Because primary reason is that right now we are still poor, and concrete offers low-tech, a lot of low-tech jobs, and that's why it turns out to be cheaper. But as we climb up the ladder of development, economic development, we will see that concrete will not be as attractive an option for very long. Okay, so there are varieties of concretes. I don't want to go into too much detail what matters to us primarily, because this is a structural steel design class, right? So we will focus primarily on the steel that we have to deal with. But also we should be familiar with other types of steels. And this is not an exhaustive list. Actually, I was preparing this list. The list was so long, actually, I was trying to go to various sources. And there are so many types of decorative types of steels which are used. And for every industry, there is a different variety of steel that is used. So there is, of course, no point in developing an exhaustive list. Of course, some of those things you have to learn on your own. So carbon steel is the most common type of steel that we deal with, that we see every day. So so of course, carbon steel is your rebar steel is also carbon steel that is used in the reinforcement bars. Of course, structural steel. So all your steel that is used as structural members, right? So bridges, towers, all those things, those are all structural. All that is carbon steel, or in other words, mild steel. Okay. Now, carbon steel also has a number of varieties, and one variety is called mild steel. Actually, not all carbon steels are mild steel, but often they are used interchangeably. So one should be careful about that difference. Then there is alloy steel. So if you replace carbon, or if you try to remove most of the carbon and replace it with some other alloys, then you will get different types of properties. So you can say that the subsequent, for example, stainless steel is one example of alloy steel. So if you add some other for example, chromium or nickel in high quantities, then you will get stainless steel. So stainless steel has very good anti-rusting characteristics, and also it has very good hardness. So it is, what is the meaning of hardness? A material is hard.
Resistance to abrasion.
Resistant to deformation.
About
No,
abrasion. Abrasion.
Resistance to deformation, resistance to abrasion, strength, anything else?
Scratch. Abrasion.
Scratch. Yeah. Correct. So those who said it is resistance to abrasion or scratch, that is the correct answer for hardness. So when we say diamond is the what kind of material? We have been told this thing from, I think, from the second grade, third grade onward. What kind of? No, like diamond has the
Hardest.
one superlative is used. Hardest, right? Is it the strongest material?
No, hardest.
Hardest material.
Hard material.
So diamond is the hardest material. It's not the strongest material. And there is a very clear difference. Can you mute your mic? Somebody's mic is open. Good, thank you. Yeah. So diamond is not the strongest material. It is the hardest material, right? So hardest material basically means when any structure has some kind of a crystalline structure, let's say, any material has some kind of a crystal. The crystal shapes are such that it's very difficult to chip off a few molecules from the edge. So, and diamond has that kind of a, but graphite does not. So graphite is very easy to chip off, right? So both of them are made of carbon, but it is just the molecular structure is such that graphite is very easy to chip off, whereas diamond is very, very hard to chip off, right? So that makes diamond a very hard material, right? Not the strongest material. It is not really the strongest material. There are much stronger materials, right? So stainless steel may have higher strength than normal steel or carbon steel normally used, but more importantly, it has a higher hardness. So the surface cannot be damaged easily, okay? And that is the definition of hardness. So you cannot scratch the surface easily. Same thing with diamond. So that's why diamond can be used for creating scratch or cutting other metals, because when you do that, the other metal gets damaged, not the surface of the diamond. Okay. Also, you can make various types of tool steel. So the tool steels are the type of steels which are much harder. So carbide steel is one type. So usually you have high carbon content and some other alloy materials, tungsten, etc. So tungsten carbide steel is commonly used as a tool steel. So it also has a very high hardness and very high strength. Okay. And also in addition to that, sometimes you may have to do some kind of a temperature treatment. So you can change properties of metals in two ways. One is by mixing other metals, right? So you can make alloys. And another way, metals or non-metals also, carbon also changes the properties. So you can mix other materials, other molecules. Alternatively, what else can you do? You can also do a heat treatment. So as you heat these metals, most of the metals, they change their molecular structure. And as you cool it down, again, they change their molecular structure. And the way you heat it and the way you cool it, that governs how much strength you will be left with at the end. And there are some ways you can modify the material properties by heating and cooling. Okay. Then there is one property which is weldability of any steel, and for that also you have to be careful about what kind of alloys you have. So not every steel can be welded. So there are some steels which can be welded. Typical carbon steel under low carbon content can be welded, but steels with high carbon content cannot be welded. Okay. Then there are some older varieties of steel which were commonly used in the past. Now their usage has come down quite a bit. One was cast iron, and the other one is wrought iron, right? So cast iron and wrought iron, the difference between the two, they are both steel, right? See, iron we understand is actually an element, right? All of us should understand. So as soon as you mix any carbon into it, it becomes steel. Okay, so it's not iron anymore, but these were called cast iron, wrought iron. Okay, so what is the Hindi word for iron? Does anybody know?
Loha.
Loha, right? I'm not 100% sure whether that is actually Hindi or like that's in Sanskrit derived or whether that is Urdu derived. But yeah, I mean, Loha is the commonly used word. Then what would be the Hindi or Urdu word for steel? Anybody knows? What is it called? What is steel called in Sanskrit or Hindi? I bet everybody, all of you know. You're just not able to recall. Ispat, right?
Yes.
Yeah, so all of you must have heard of Ispat. So Ispat is the, I think, Sanskrit derived Hindi word, and in Urdu it is often called Folad. Okay, so that is the difference. So iron is basically your element. So when you have pure Fe element, that is iron. And as soon as you mix some impurities, especially carbon, it turns into steel. And there were two varieties. One was cast iron, which was commonly used. Still, it is used in certain applications. So, for example, often, where have you seen its most frequent use? Cast iron?
Manhole covers.
Manhole covers, very good. So, manhole covers are made of very thick amount of steel, and it's commonly used as this thing. So, wherever you can see a seam, so if you look closely on a manhole cover, you can see that there is a kind of a seam where there was a leakage of steel, molten steel. So, which is different from a kind of a line that you will get through welding or through rolling process. So it is not made with the welding, rolling, or any kind of machining. It is basically cast. So cast iron is basically you take molten iron and you cast it into a mold. Okay, so you pour that in a mold and you get that shape. So that's how cast iron is made. And you don't do any processing after that. So you don't mill it, you don't roll it, you don't do anything. That shape is the final shape. Wrought iron is also another type of iron which was much more malleable than cast iron. So cast iron used to have relatively high carbon content, and therefore it was very brittle. It was not very deformable. Now, brittle, I mean, we might not have seen its brittleness. I mean, manholes are there, but we don't see them breaking very often because they are made very, very thick amount of steel. And we never subject them to the stresses which are beyond the yield point. But if you do that, if you subject them to stresses beyond the yield point, then you will see that how brittle they are. Wrought iron is another type of basically steel which has very low carbon content, and very low carbon content makes it very malleable. Okay, and there are some anti-rust properties also. And does anybody know or know some example of where you might have seen some wrought iron being used?
Decorative, sir.
Decorative. Railings. Railings, yes. So if you go to any old cities, say Paris or London and so on, and if you see those lamps, lamp posts, right? So there is a lamp on the top and there is a kind of pole, and that pole would have some kind of a decorative features, and all that is made with wrought iron. So because it was very malleable, they were able to heat it a little bit and deform it in various shapes and forms. And benches, even Eiffel Tower, it's made of wrought iron. Because Eiffel Tower, if you look closely, it has a lot of these decorative features. Okay? So it has relatively low strength, but it is very malleable. So, but nowadays it is very difficult to get enough quantity of wrought iron that you can use actually. So cast iron is used more frequently, still more frequently. Okay. So I will not talk about the rest of the types of steel now, stainless tool steel, because they are not relevant for this class. It is the carbon steel that is of most significance for this class. So about 90% of the steel that we see every day is all carbon steel. Okay. And then within carbon, you may have three varieties. You may have low carbon, you may have medium carbon, you may have high carbon. And as you increase the carbon content in steel, what happens to the strength? Strength increases, but ductility increases. Right? Yeah. So then in low carbon steel, you will have up to between 0.05% to 3.3% carbon content. And but there may be some other alloys as well. Some nickel or chromium may be added. So this is the most common type of structural steel, that is low carbon steel. And what is it used for? It is used for main structural members. So your beams, columns, I sections, ISMB sections, angle sections, they are all made of this low carbon steel. Okay. Also known as mild steel. So mild steel is a very kind of a generic term which is typically used for steels up to 250 or sometimes up to 300 MPa yield strength. So therefore, a more technical designation would be low carbon steel. Okay, and it is decently malleable. It has a strength in the range of ultimate strength in the range of 410 MPa to 780 MPa, and these are all given in different codes. I will go to those codes in a minute. Okay, and most of these steels, if you keep the carbon content low, most of these steel tends to exhibit a very clear yield point. So there will be always this yield plateau. So all of you are familiar with the stress strain plot of steel. So it has a linear elastic part, then there is a yield point, right? And then there is this strain hardening part. So this yield point, and even within the yield plateau, you may have kind of a high yield and low yield. So all these things can be very clearly seen if you keep carbon content low. As you increase the carbon content, you tend to lose that plateau. Or if you do any kind of strain hardening, so for example, if you can in deformed bars and so on, you don't see that. So that is a separate issue. Okay, and medium carbon is the other type of steel which has higher carbon content, more than 0.3% up to 0.6%. And this type of steel is often used for making boards because you have higher strength and ductility requirements are not that important. Making threaded rods, which are mostly used for tension. Crankshaft, which is meant for, you know what a crankshaft shaft is? Anybody knows where a crankshaft is used?
Mechanic engines.
Yeah, so
Flywheel.
what kind of flywheel? Sorry. Somebody said flywheel, right?
It's a rotating shaft.
Rotating shaft. Yeah. So basically, it is a rotating shaft, and what kind of stresses is it subjected to, or what kind of forces is it subjected to? Torque. Right. Yeah. So very good. So crankshaft is basically because pistons in any engine provide you linear movement, right? Whether it is diesel engine or it's this turbine or this kind of a gas engine, what is it called, the steam engine or whatever. So it provides you a linear movement, and that linear movement, and if you have several pistons, then all that linear movement has to be converted into a rotational movement, right? So because our wheels require to be rotated at the end, or whatever generator you have that has to be rotated. So that linear movement of the piston has to be translated into a rotational movement, and that job is done by a crankshaft. So a crankshaft is usually not a straight shaft. It has some kind of this bent shapes, and that's where the piston is attached to. And when the piston pushes and pulls, then that leads to the rotation of the shaft. So it is subjected to high amounts of torsional demands, forces. Okay. And so typically they have high strength, but they have low ductility. And that is okay because we usually tend to use all these parts. So whenever we are going for high strength requirements, we design our systems in such a way that these will never be subjected to yield point. So if they are never going to be subjected to up to the yield point, then ductility really is not. Ductility is not really a major requirement. Okay, so only when we are expecting them to be subjected to yield point at some point, then we have to worry about ductility beyond that. And then you have high carbon steel also. So these are useful for high strength and hardness applications, but they have very low ductility. So such kind of requirements can come in very high stress applications, such as suspension springs in a vehicle. So the shock absorbers, they are made of high carbon steel, right? So that might be surprising to you, right? Why are the shock absorbers, which are supposed to be subject to a lot of shocks, why are they made of high carbon steel? When we know that high carbon steel has poor ductility performance, right? Because again, even though shock absorbers, they undergo large deformation, but we make sure that those deformations are all elastic. So the element itself is never subjected to beyond elastic limit or beyond yield point. So then you can use it as for springs or so on. Right. Typically, most of the carbon steel that we use or low carbon steel that we use, it has carbon and it has many other elements. It may have sulfur, phosphorus, manganese, silicon, nickel, chromium, aluminum, molybdenum, vanadium, and so on. Okay. Now, what happens is that there are codes. There is one code, IS 2062, which specifies how much of carbon can you have and how much of other metals can you have. And what happens if you put too many of these metals, other metals, is that you compromise the weldability. So from weldability point of view, you need to keep the carbon content low, because if you increase the carbon content, the material becomes less ductile and less weldable, okay, and more brittle, less tough. If you keep the carbon content low, you increase the ductility, you increase the toughness, you increase the weldability. So steel with low carbon content is more weldable than the steel with high carbon content. Okay. So carbon is one factor, but in addition to carbon, also you have to monitor other metals. So here there are some expressions, some formula given in the code, which lets you calculate the amount of equivalent carbon. Okay, so where you put the carbon content, manganese content, chromium, molybdenum, and vanadium, and so on, and you put all their content, divide by the respective factors, and if the total value comes out to be less than, I think this formula is wrong here. Let me check quickly. This should not be, bracket should not be before C, in my opinion. Let me check. This is IS 2062. Yeah, sorry. So that was only manganese divided by 6. Can you see this formula here? Equivalent carbon is C plus Mn by 6. That was a mistake here. If you had a hard copy of the lecture note, you could have easily made this correction. So this is a minor correction here. I'm sorry, I didn't realize it before, but as I was explaining. Okay, so carbon equivalent is carbon content plus whatever other metals you might have. You divide them by the respective factors and you calculate the carbon equivalent. So if you have too much of these metals, and their names are all written here. So if you have too much of these metals, they will affect the weldability, and you have to keep equivalent carbon content less than 0.45%. Okay, otherwise the weldability is compromised. In addition to adding these different metals and different constituents to steel, you can also change the properties of steel by doing some kind of a heat treatment. So hot rolling or cold forming, that is one type of a treatment, right? So you know what hot rolling is, all of you must know, right? How is this ISMB or ISA sections made? ISMB is Indian Steel Medium Beam, right? ISMB. M is medium, steel is, I think, S is probably steel. Yeah, so Indian standard or IS could be Indian standard, and then medium beam, ISMB. So ISMB sections, for example, so they are all rolled sections, right? So they are all classified as hot rolled sections. I will talk in more detail about these sections later. So usually what happens is that you heat steel to a very high temperature, or like after a heat is treated, it is mostly kept in a kind of a this square shaped billet or something. I think it's called billet. So it's a square-shaped kind of a steel log, if you say, if you may call it that. So it's a solid steel piece of steel which is heated to almost 1200 degrees centigrade. So at 1200 degrees centigrade, it has become very malleable, very easy to deform. And then that steel billet is passed between two rollers, and slowly it is deformed to achieve whatever shape you want. And rollers are placed in such a way. So sometimes for angles, you may have to put rollers in such a way so that something like this. So if I want to create an angle section, so I may put a roller with this shape and another roller with this shape, right? Sorry. So the two rollers are rotating about these axes, and then that steel will be passing through this portion, and it will take the angle shape. Correct. Similarly, you can put one roller this way, rotating this way, and another roller rotating this way. In the other direction, sorry. Here also it was in the other direction. Right. So if you have that kind of a section and you pass and you gradually you bring these two rollers, this roller and this roller, you gradually bring them closer. So what will happen? Any steel piece that I had put here, that will start to bulge out, right? And slowly it will take the shape of an I section, and you can control it by putting another set of rollers on top and bottom. Right? And you rotate them constantly so that, and apply the required amount of pressure so that you get the desired shape. That process is called hot rolling. Similarly, there is another process that is called cold forming, and through which you can often develop very thin steel sheets, and then you can galvanize it, and they are often used. Dr. Madhavan works especially in that area. So these processes have some effect on the mechanical properties that these materials develop. So hot rolling usually makes it more malleable, steel more malleable, because it is being deformed as it is cooling down. So the billet starts from a very high temperature of 1200 degrees centigrade, and as it is passing through a series of rollers, one after another, the temperature is slowly cooling down, and as a result, it becomes relatively malleable. Okay, and by the time it achieves its shape, also as a part of this process, it develops a lot of residual stresses. There are some explicit heat treatments, right? So one such is annealing or normalizing or quenching. Okay, so the difference between the three is basically in all three of them, you have to heat the steel element. So first you heat it to a particular temperature, then you let it cool down. And the way you let it cool down governs what will be the residual strength. So if you let it cool down very gradually in a very controlled manner so that the entire specimen is almost at the same temperature, uniform temperature. So you heat it to 900 degrees centigrade and control in a controlled cool down in a very controlled environment where the temperatures are coming down very gradually and uniform temperatures are maintained. Then it is called annealing, and as a result, you don't achieve very high strength. The strength remains as it was before, but you gain in ductility. Normalizing is basically the process where you heat it to 900 degrees centigrade and then you leave it in the open atmosphere to cool it. So you leave it in the workshop to cool it under the atmospheric conditions. And that is also relatively slow cooling, but also it leads to some thermal gradients, some non-uniformity in the temperature. And as a result, you get some level of hardness, some level of higher strength, but also some level of ductility. Quenching is the process where you cool it down suddenly. So you heat it to 900 degrees centigrade or higher, and then suddenly put it in a bucket of water, right? Or suddenly pour water on that steel. So suddenly, if you let the steel cool down, then there is something called martensite that is formed, and that changes. So that is basically, martensite is another structure of molecules within within the metal, which provides you it very high strength. So typically, a steel that is cooled down slowly, that if you look at microscopically this and polish the surface and look at it microscopically, this is how the structure will look like typically. So you would have this some gaps in between, some impurities in between, and then you would have a more or less uniform type of a structure. And this light structure, light color, whatever you see, that is ferrite, right? So that is one type of structure, molecular structure within steel. But if you let it have this kind of a rapid cooling, quenching, okay? So as a consequence of quenching, you will be, so when you heat it, the ferrite turns into austenite, and if you let it cool down slowly, again it goes back to ferrite. But if you cool it down suddenly, then it goes to martensite. And martensite structure, if you polish it again, another specimen, you cut it, you polish it, you look microscopically, the structure looks somewhat like this. So you will see a lot of tiny microscopic needles kind of forming, and these needles almost look like ice needles, right? So if you let ice frost or let water frost, it forms this kind of needles kind of a thing, and which basically provides it very high level of brittleness. Okay, so higher strength but more brittleness. Okay, what are the material properties? I'm sure mechanical properties of steel, I'm sure all of you already know most of these. There is a small correction in the slides. Modulus of elasticity is, I think, mentioned incorrectly. It should be 200 GPa or 200 into 10 to the power 3 MPa. I think, or 2 into 10 to the power 5 MPa. I think I had mentioned 200 into 10 to the power 5 MPa. So that correction you can make, please. Poisson's ratio is 0.3, but you have to be mindful that Poisson's ratio is elastic, right? Under elastic conditions, the Poisson's ratio is 0.3. What is the Poisson's ratio under plastic conditions for steel? 0.5.
0.5.
Yeah. So what does that mean?
That if you give one deformation in one direction, then half of the deformation in other direction.
Correct.
No.
So is there any volume change? How much is the volume change in steel in that case?
No volume change, I think.
Yeah. So it's a three-dimensional, or let's say your specimen is three-dimensional. When you have a Poisson's ratio of 0.3, if I may draw it here. I'm still learning how to draw on this thing, so please bear with me. Yeah. So what Poisson's ratio basically means is that if I apply a strain of, let's say, 1, and of course one strain is very large, but I'm just for example, okay. So the deformation in this direction, so if it moves by 1 in the vertical direction, let's say, so in the two horizontal directions, the specimen will, or this sample will move, right, deform. So it will shorten in this direction, but it will elongate in this direction, correct? And how much will that elongation be, is governed by the Poisson's ratio. So if the Poisson's ratio is 0.3, that means if you push it by 1.0 here, then it will move out by 0.3 in both these directions. Okay, so now if you calculate the revised volume, you will see that there is a volume reduction. Okay, however, if this specimen, the same specimen, and by the way, this is a very crude example, these are not exact numbers, but almost the same thing. So and it moves laterally by 0.5% in each direction, and you do the volume calculation, you will see that the volume is almost the same. And actually 0.5 stands for exact same volume, correct? So basically what it means is that under plastic conditions, we typically consider the volume to remain unchanged. In other words, the Poisson's ratio changes to 0.5. And if the Poisson's ratio is 0.5, then can we calculate the shear modulus from elastic modulus? Elastic modulus is anyway 0. So, okay, ignore it. Okay, so we have to be mindful of the Poisson's ratio that we take under plastic conditions versus elastic conditions. So as you may know, As you may know, typically if I have any structural member, and this side is tension, so first I let it to tension, I let it yield, and then I let it unload. Okay, so this is loading. First, this is elastic phase, then this is plastic phase, and then you may have unloading phase. Okay, so in this unloading phase, you are in elastic deformations. The new deformations are all elastic. Okay, and assuming that this slope is same as this slope. Okay, so in this stage, let's say this is not a gradual change, this is a sudden change. Let's say the material behaves in a perfectly elastic plastic behavior. And so in this stage, up to here, up to this point, you have a Poisson's ratio of 0.3. Then from here to here, you have Poisson's ratio of 0.5. Then again, from here to here, you have a Poisson's ratio of 0.3. Okay, so this is something that you have to be mindful of whenever, let's say, you are doing some kind of a modeling or something. And if you are using any inbuilt models in, let's say, one of the finite element softwares, and you're defining it as a plastic behavior, automatically the software will assume a Poisson's ratio of 0.5. But sometimes if you're developing a tool or if you're defining your own material, let's say UMAT or something, you may have to be mindful of that, and you have to make sure that it is doing that. Okay, you know the relationship between the shear modulus and modulus of elasticity, right? So what is shear modulus? Shear modulus is if I have a piece of metal like this, right, and I subject it to these stresses, and in order to keep it in equilibrium, otherwise it will start rotating, I apply corresponding stresses in these directions, then this metal will deform, right? And if I, let's say, keep this surface unmoved, then it will rotate this way. Am I right? So this surface will rotate by this much angle, and this angle, I can call it gamma. Okay, so how much force I applied and how much stress it caused, so that stress will be called tau over this surface, right? The force applied over this surface will be called tau, force divided by the surface, and that tau and gamma relationship, so tau divided by gamma is my, what is it? Shear modulus, right? So the shear modulus and Poisson's ratio and elastic modulus are related together, and they are related by this expression. G shear modulus is equal to E divided by 2 times 1 plus mu. Okay, and you can calculate it from this expression. So this is always approximately. So in this case, it is 2.6 times, right? 1 plus 0.3 is 1.3. So 1.3 times 2 is 2.6. Yeah, so about 2.5 times smaller than your elastic modulus. Thermal expansion, steel, like any other material, most of the materials expands when you heat it, and thermal expansion coefficient is 1.2 into 10 to the power minus 5. I often like to give this thought experiment for my students to work on. So this is basically a strain value, right, per degree centigrade. What is the unit of strain? Unitless, right? Yeah, so same thing here. It is 1.2 times 10 to the power minus 5 is the strain per degree centigrade, thermal strain per degree centigrade. So let's say I have a mild steel with 240 MPa yield strength. Okay. So my 240 divided by, let's say, divided by E value, right? E is this much. So if I divide by Fy by E, what do I get?
1.2.
Yeah, what value is that? Or like, what is the quantity? It is GPa. Correct? That is the strain value at which it will yield. Right? And I found that my alpha, which is also a strain value per degree centigrade. Can you mute your mic, please? I can hear a lot of background noise. Thank you. So alpha is equal to 1.2 into 10 to the power minus 5 per degree centigrade, right? So if can you think of something happening in between these two? So if I increase the temperature by say 100 degrees centigrade, right, then how much strain will I generate? How much thermal strain will I generate? I will generate the same amount of thermal strain as my yield strain. Correct? So this was my yield strain, and at 100 degrees centigrade temperature rise, my thermal strain, so I'll call it T at 100 degrees. It's very difficult to write straight. Excuse me. Thermal strain at 100 degrees temperature rise is equal to 1.2 into 10 to the power minus 3. Okay, unitless. That is meeting my yield strain value. What does that mean? Can anybody tell me the physical significance of this observation? Anybody? What it essentially means is, anybody wants to try? Please tell me. No, I cannot hear you.
Sir,
Yeah.
sir, if you are increasing the temperature by 100 degrees Celsius,
Yeah.
you are getting the strain which is equivalent to the one which is yielding the material. If the
Yes.
material is fixed on all the sides.
Yes, exactly. So if I take, let's say, a piece of metal which is fixed from both ends can't move. This end cannot move, this end cannot move, and I increase the temperature by 100 degrees centigrade of this rod. Okay. As soon as I do that, that piece of the metal, the entire length of this piece will yield. Okay, 100 degrees centigrade is a small temperature, right? We often see that around us in equipment, etc. We can very easily see the temperature rise of 100 degrees centigrade. In fact, in our let's say any structural system, let's say a bridge or something, in any kind of areas such as like Rajasthan or Punjab or some such places where you get decent amount of cold as well as a lot of hot weather also, you can very easily see a temperature difference of up to 60 degrees centigrade in hot sun, right? So a temperature difference of 60 degrees centigrade delta is equal to 60 degrees centigrade. Imagine the amount of stresses you can bring in just from the thermal strains, right? While this is true, I mean, of course, we did that, and these numbers all not unreasonable. I mean, 240 is slightly small, but it just made our calculations easy. Otherwise, I could have taken 250, did not have changed things too much. The 100 degrees centigrade change can bring the material to complete yield, and we do see up to 60 degrees centigrade temperature change all the time, right? So, for example, in a typical city in Punjab or in a typical village in Punjab, you can see winter temperatures dipping to almost 0 degrees centigrade, and summer temperatures going all the way to 55, 56 degrees centigrade. And if the structure is sitting in hot sun, the structural temperatures will go beyond, especially steel and so on. Their structural temperatures will go beyond 60 degrees centigrade, right? So, but we never really, seldom worry about these stresses, but we are almost eating into, like, almost 60% of the strength will be eaten up by the sun itself, by the heat, the change in temperature itself. Why don't we do that? Anybody has any answers? Of course, those structures don't collapse every day, right? If that was the case and the heat itself was consuming 60% of my reserved capacity, the structures must be collapsing all over the place. But they don't.
Because maybe at the time
Two people are responding. Let the first person respond first.
because at the time of building, construction, generally construction at room temperature, sir. It's only the rise. How much rise? Generally, we don't construct at 0 degree. From 0 degree to, if we construct to 50 degrees centigrade, then it might have get affected.
Okay.
So it's the median temperature at which we construct. So maybe.
So yeah, that's a valid point, but it's not really the answer. The answer you gave is not wrong. It's just not answering my question. Okay, so what his point is that we actually construct some when the temperature is somewhere between 20 to 30 degrees centigrade. So when at that time we made sure that everything was stress-free at 30 degrees centigrade. So from 30 to 60, we have to worry about. So basically, you're eating up 30% of the reserve capacity still. So when you go from 30 to 60, you're eating up 30% of the reserve capacity.
So, but
As
if
per
we allow
your
thermal
argument.
expansion,
Sorry, repeat your answer, please.
so if we allow thermal expansion, there will not be any stresses.
Exactly. So what happens is that most of the structures, they have some kind of a give. So for example, if you have, you must have all heard of this railway lines, right? The rails for the trains. So those rails do buckle all the time. So you have to find a way so that they can undergo that kind of stress. So those rails do undergo 60% change in, like 60% of the yield stress, they reach that level of stresses. But other than those structures, typical structures that we deal with. So for example, when we are designing a tower or a building and a beam wants to expand, it is not really subjected to fixed boundary conditions at both ends. It is supported on columns, and columns have some kind of a flexural flexibility. So when the beam wants to expand, the columns let it expand a little bit. Similarly, you have a tower. Members of the tower want to expand. They can expand. Nobody is stopping them. They will just the tower will become like what 0.12% taller after 100 degrees centigrade rise, but who cares, right? Similarly, for the bridges are supported on bearings where you have roller supports, so you allow them to expand. So these boundary conditions are not real; these are imaginary boundary conditions. But we should be mindful of this possibility. And when we design structures, we should know that if we provide too much of rigidity to the structure, then there may be stresses developed with a very large stresses developing with a very small change in temperatures. Okay, I hope I had made my point clearly here. If you have any questions, you can always email me, contact me otherwise. Okay, so typically when you test steel, we test steel for mechanical properties in tension, right? There are some other properties that we test it for, but the most commonly used test is the tension coupon test. Also for rebars, you don't prepare a coupon, you test the rebar directly. But for steel, if you have a steel plate or if you have a hot rolled section, you have to cut a coupon from that hot rolled section and test it. Okay, and IS 2062 gives you the expected strength values for any type of steel. So for mild steel, for example, typically what we call mild steel is your Fe410 steel, which has a yield stress of 250 MPa and ultimate stress of 410 MPa. Similarly, you have ductility requirements also. They are also given in IS 2062. And that basically depends on the gauge length, but of course that gauge length depends on the cross-section area. For that, you have to follow the test protocol, and the typical ductility requirement should be between 20 to 25%. And then there is a toughness requirement also. The toughness, I'll talk a little bit in detail about the ductility test and toughness test. So we had discussed about this typical stress strain behavior here, right? So you can see this plot, right? This is a typical coupon test. So what we do is, let's say I have an I section. A plate is an I section which has several plates. So it can be a hot rolled section, it can be a welded section. If it's a welded section or a hot rolled section, what I need to do is, there are coded provisions which tell you how to do the test. So for that, they tell you where to cut the sample from. So first you are required to cut a strip of this plate. I can't draw it very clearly. So let's say I cut this strip. You can see this strip that I have cut from this. So you cut that strip. That strip looks like this. It is a straight strip. I mean, I cannot draw it straight. So this is how the strip looks like. Then we need to cut a dog bone shape on this one. Okay. This is not to proportion, of course. So we cut it into a dog bone shape. This is called a typical tension test coupon. Okay. And the requirements for the dimensions, etc., are given. There is some problem here. Anyway, you get the point. So this is how a typical coupons looks like. And then the wider parts are placed into a, the wider parts of this coupon are placed inside the grips of a typical UTM, and then you pull it in tension. And as you do that, you develop this kind of a stress strain plot. Right? So this is the linear elastic part, then this is the yield plateau, and then you may have a strain hardening part. And at some point, the rupture takes place. Right? So when the part breaks into two, the coupon breaks into two pieces. So the strain at that time of rupture. So what happens is that we have to, before we start the test, we have to put a some kind of an extensometer or some kind of a dial gauge or something which measures the movement between 2 points. And where we place this, the two locations in between that we place this extensometer is actually called the gauge length. Okay, so we measure how much deformation it has undergone before it ruptured, and then that divided by the original gauge length, that determines the ductility of the specimen. So gauge length depends on the original cross-section area, the square root, multiplied by 5.65. These many millimeters of gauge length is used. And then ductility is basically a percentage of that original gauge length. So how much change in length it had. Okay. And at least 20 to 25% ductility is required. There can be some other ways of measuring ductility. Often for some other materials which are relatively brittle, we don't always wait up to rupture. We say that when the strength drop is, let's say 20% from the peak, that is the definition of my ultimate stress or ultimate strain or epsilon max. So you can define your epsilon max in various ways. For steel, usually we use rupture point. There is another parameter that is of very significant importance, that is known as toughness. So toughness is basically the behavior of materials under impact loading. So there may be metals which or materials which may be very strong under gradual loading conditions, but under impact loading conditions, they may perform very poorly. So toughness becomes very important for that. Toughness is basically a measure of how much energy it absorbs before it ruptures. Okay, so it can be represented as the area under the stress strain curve, but the stress strain curve is developed under gradual loading conditions. So you cannot extrapolate that information under high strain conditions. So this toughness test has to be done at high strain conditions. Okay, and one such test commonly used is known as Sharpe V-notch test, where you take a specimen which looks like this. The dimensions are available in various codes, and then you cut a V-shaped notch in this, and then you place that specimen like placed here between two lateral restraints. And then if you push the specimen in this direction, basically this surface, this edge of this specimen will be in tension. And this notch is where the highest amount of tension will be generated, and a crack will propagate. A crack will start from here and propagate through the thickness of the specimen, right? And that's how the specimen will rupture into two parts. And the amount of energy it will absorb in the process can be determined because there is a hammer here which comes, this is the hammer, this is that hammer that comes from, that is released from a particular height. It comes down, hits the specimen, and on the other side it goes to a certain height. Depending on how much is the difference between H and H prime. H prime is this height and H is this height. So the difference between the two heights basically tells us how much energy was absorbed by the specimen, and that is a parameter that governs the toughness. So if the toughness is very high, your H prime will be low. If the toughness is low, your H prime will be almost as high as H. Okay, so toughness characteristics change very significantly at high temperature, at low temperatures, and because of that, for all kinds of steel, you have different types of grades available. So all strengths. So for example, if we are dealing with a steel which has a 410 ultimate stress, that would have Fy values somewhere between 230 to 250 based on which type of steel you're talking about. But within that, you may have 3-4 different types of grades of steel: grade A, BR, B, and C. And basically what they mean is that how good their toughness characteristics are at different temperatures. So A generally is the poorest kind, or in other words, it does not require any toughness characteristics or toughness. There are no toughness requirements to be met, which is typically the regular, our standard, our structural steel to be used, not in cold environments. Then you may have some kind of structural steel which has to have minimum amount of toughness only at ambient conditions. So you may do some level of impact test for that. Some level of impact test is required, but only at the room temperatures. Then you may have other steel which needs to be used in cold environments, and there may be shock kind of loads acting on it. Then the steel has to be tested, which is called grade B0, and this kind of steel needs to be tested under impact loading condition at temperatures of 0 degrees centigrade. And then you may also have C grade, which is the highest or most stringent type of steel, and that has to be tested at temperatures of minus 20 degrees centigrade. So for that, you have to have a cryogenic kind of a system where you can maintain temperatures of so low as minus 20 degrees centigrade and do the impact test at that temperature. Okay. These are some tables. I've taken a screenshot from IS 2062. I was talking about different materials that are allowed. Carbon is allowed, manganese, sulfur, phosphorus, silica, and or silicon rather. And what percentage of these metals are allowed, or these materials are allowed for this steel to be classified as E250, E275, E300, and so on. There are two ways. Either you can classify it as E, which is basically corresponding to the yield stress, or you can classify them as the ultimate stress, that is Fe. Okay. So if we say E250, that is basically means 250 MPa yield strength. Then within that, you may have four classifications: A, BR, B0, and C. And then for them, you have different amount of these materials allowed. So as you can always see, as you move from A to C, your total carbon equivalent decreases. So for A, you have a more lenient carbon equivalent portions allowed, but a C type or C grade steel cannot have more than 0.39% equivalent carbon. So this is the maximum value that you can have, maximum value here. Okay. So you cannot have more than 0.39, but whereas for A, you may have up to 0.42. Likewise, the restrictions are applicable to different materials in each type of steel. Again, from the same code, this is the table. These two slides are not there in your lecture notes because you could find them in the code 2062. Similarly, the steels are classified here based on their mechanical properties. So mechanical properties of relevance are ultimate stress. So this is the steel that we typically know as Fe410, also can be classified as E250. And again, for E, BR, B0, C gradations. So depending on what kind of gradation it has to satisfy a minimum amount of impact test reading. Okay, so how many joules of energy it absorbed, at what temperatures the test was done. Okay, and the important things here are, first of all, the tensile strength, that is 410, that is constant, and then the yield stress. And yield stress may vary between 230 to 250 depending on the thickness of your coupon or the thickness of the plate. And this is the minimum percentage elongation required. So 23% minimum elongation, that is your ductility parameter. 23% is basically your epsilon max. So this should be at least 23%. Okay. So far I have talked about three primary material properties, material characteristics. One is yield stress, another one is ultimate stress. Then comes the question of your percentage elongation, right? Also, I have talked about toughness, right? So toughness, you have to do Sharpe-Binot test, this one. So 1, 2, 3, and this 4 properties we have talked about. That is typically used. Also, you have hardness and all those properties, but they are not usually important for structural steel. There is one more structural property that is of relevance for us, is the fatigue behavior. Okay? And that too, high cycle fatigue. So there are two types of fatigue behaviors that can be studied. One is low cycle fatigue. What low cycle fatigue basically means is that you do only a few, you push a structural element under cyclic loading, but every time you go beyond the yield point, then you will end up with low cycle fatigue. Low cycle fatigue basically means that material should rupture or crack or fracture within a few cycles, maybe a few tens of cycles or a few hundreds of cycles. High cycle fatigue basically means is that a material may rupture under a very large number of cycles, so a few thousands or a few million cycles. Okay? And this is often observed, this kind of a high cycle fatigue behavior is often observed when you subject a metal, especially metal and other materials too, to a large number of cyclic loading conditions. So for example, one common example is the axle of a wheel. So if you have a wheel and it has an axle, the axle is constantly rotating, right? And let's say, I don't know whether I can draw it. The pen is not working for some reason. Okay. So I'm trying to use my gesturing. So here I cannot draw there. So let's say I have an axle of a wheel, and which is supported. So it is these are the two wheels at the end, and there in the middle there are 2 points where the car load is or vehicle load is coming onto the axle. So if you can imagine, this looks like almost like a 4-point bending problem, right? You have 2 supports where the wheels are, and there are 2 points of loading, right? So this is a 4-point bending problem. But the only challenge here is that the axle is rotating. So the part that was in tension, let's say the bottom of that axle, so you have an axle and it bends, let's say this way, and the bottom of the axle is in tension. But soon the axle rotates, and when it rotates, what happens is that the top, instead of the bottom, the top goes into the part that was in bottom goes to the top and becomes in compression. So the axle is constantly subjected to tension compression cycles. Okay, but we make sure, always the engineers make sure that the stresses are still very low in comparison to the yield stress. So it is never reaching the yield point, but still what happens over several hundreds and million cycles, there may be a risk of a fracture in this piece of metal. So this is typically known as high cycle fatigue or just fatigue often. So basically what happens, it starts with a small crack. With each cycle, the crack keeps growing and growing in size, and at a certain point, that micro cracks develops into a full-blown crack and then rips through the element. And this kind of failures have been observed in bridges, because bridges are also often subjected to cyclic type of loading conditions because of the traffic. Okay, so there are various examples you should study about. So for toughness characteristics, I think that why the Titanic ship had sank. If you read that example, read the history of the way the methods that were used to make the Titanic ship, the steel that was used, and why had those ships. So it was not just the Titanic. There were a couple of other ships that were made using the similar technology, and they had all had a very bad history. And I think that technology had something to do with them. Toughness characteristics had a role to play there. Also, fatigue characteristics, if you want to see how fatigue can lead to devastating failures, there are hundreds of examples available. You can read about this de Havilland comets in 1954. So this was basically corners. This was an aircraft, and the corners of this aircraft were developing very high stresses, and the cabin pressure, because in an airplane you have to pressurize the cabin from inside, and outside air pressure is very low. And over a few cycles, after several flights, these stresses were reversing constantly and going into cyclic loading, and that led to this fracture or fatigue fracture. Also, you might often see that this asphalt pavement, this blacktop pavement, often develops cracks, right? So many a time we attribute that to the rains or the poor drainage conditions and so on. That might be true, but even if all those things are taken care of, they have a limited life, right? They tend to crack and they tend to give out. So one of the major reasons for those, because that's a very plastic kind of a material, it is bitumen, right? So bitumen is very plastic material. Still, under normal working conditions also, under normal traffic load also, because of it being subjected to several cycles, it also develops fatigue cracks. And those are the tiny cracks that you see even in this bituminous pavement is actually are all fatigue cracks. And those cracks actually lead to the deterioration of the blacktop surfaces. Okay, I think I have last 5 minutes. I'm sure all of you are familiar with this typical stress strain plot. This is the yield stress. This is called ultimate strength. Then you have a failure point, right? And failure point is what defines the maximum elongation, right? Percentage elongation, and that is what defines the ductility behavior. Now, in the next class, I will try to talk about. So, for example, we know how to do the test in a uniaxial direction. So you prepare a coupon of this shape, which is also known as dog bone shape. These wider portions are put inside the grip, and then you pull it in tension, right? So when you pull it in tension, you are not applying any stresses in this direction or in the out of the plane direction. There is no stress applied. It is only in the single longitudinal direction you are applying the stresses. So that is called uniaxial stress. And under uniaxial stress, it is very easy to calculate the failure stress. So if my failure consideration is yielding, I can say, okay, so I test this, I get this yield point, that is my failure stress. That's very easy to find. If my ultimate stress is my requirement, then I can get the ultimate stress, no issues. The challenge is if the coupon, if it was not a coupon, it was a part of a beam or a column, then I cannot say with guarantee that the stresses are all uniaxial. The stresses might be multi-axial or triaxial. So if the state of the stress is more complex than uniaxial, then at what stress will it yield? So the same piece of metal which was yielding at, let's say, 250 MPa in uniaxial testing in a UTM, I put that in the universal testing machine, apply the uniaxial tension, I get a 250 MPa yield strength. But what happens when that piece of metal is sitting inside a big equipment, a big chunk of steel, and then various types of stresses are applied? Then at what stress will it yield? That's where the failure theories come into picture. And I will talk about that in the next class. So with that, I will stop here. I would like you to ask if you have any questions. Please let me know.
Sir, so there is one doubt. Sir,
Yeah.
Sir, reinforced concrete structures are regularly subjected to, and in those structures, corrosion is a big problem, corrosion of reinforcing bar. As we
Yes.
know that stainless steel is, I mean, it's anti-rust, and so did anyone tried,
Yeah.
did
Using
researchers?
stainless steel for, yeah. There is plenty of literature available. Looks like, see, what happens is that concrete typically itself has these properties which are anti-rust properties, because you create a kind of an alkaline environment around steel, right? If you measure the pH value of concrete, it is very high.
Yes, alkaline.
So yeah, so you create an alkaline environment which is kind of automatically prohibits or kind of resists the possibility of rusting, right? Because steel tends to rust and not in alkaline environment, it tends to rust in acidic environment, right? So generally regular steel also should perform pretty well, unless you either you have a very aggressive environment or you have wide cracks where the things like where the moisture can get in and then compromise, right? So people have tried to use, there is a lot of literature available, I'm sure. I mean, lately I have not studied anything, but this is something which people have tried and kind of given up on it, because the cost of using stainless steel was not really properly offsetting the benefits of low corrosion properties. So instead of in order to avoid corrosion, people have in fact moved to this
Cathodic protection.
yeah, these things, or otherwise just like these modern materials like CFRP, etc. CFRP bars. So they tend to they have no corrosion issues and they have various other advantages, and lightweight also. So yeah, stainless steel never picked up. I don't exactly know what might have been the final argument against stainless steel, but my gut feeling is that probably just the cost is not really offsetting the advantages. Yeah. Or advantages are not offsetting the cost. Anyway, sorry. Yeah.
Thank you, sir.
Any other questions with regard to steel or what we discussed today? Guys, you guys have to speak a little bit more. Ask some questions, please. Or maybe what I'll do is that 40% marks I have assigned for, right? This thing, that marks will be only for asking questions. Okay, the quizzes thing, right? 40%. That I'll make it for only asking questions. Is that okay? Come on, somebody must have had some questions, right? No. Okay. Yeah, you have something to ask.
You had one of the things. Sorry.
Krishna Katyal, tell me.
So there was one of the things you just mentioned, like in the bridges, once you were saying the span increases after some length, you usually start going for steel structures rather than concrete. So
Yes,
can you just
yes.
elaborate what did you mean by that? What span and how does it affect?
Okay, yeah. So basically, I mean, bridges are of various kinds. The bridges I was talking about are the girder bridges. So where you use a girder to resist the bending moment. Then once you get into the truss bridges, again, trusses are possible only in steel. Trusses are not, I mean, concrete trusses are very, very uncommon, only for artistic purposes or something. People sometimes make concrete trusses, but otherwise concrete trusses are very uncommon. So then, of course, the steel is the only option. And then you go for cable stayed bridges and so on. Then you have more complicated systems. So I'm not talking about those. I'm talking about bridges which have girder primarily as the structural system to resist the bending moment. Now, within that, what happens is that pre-stressing is the technology that is typically used for girders, right, in concrete. So with pre-stressing, what happens is that the requirements of pre-stress forces become beyond a point. They become so high that your concrete strengths are not able to meet the requirements, and basically you end up with basically you reach the limit of concrete strength in a way. So therefore, with the pre-stress concrete, there is mostly, if you look at NHAI guidelines, railways always relies more on steel, but even NHAI, you can see that typically they would go up to, I think, I don't remember the numbers off the top of my head. I think something like 90 meters or 60 meters, something like that. There are some limit. So up to 60 meters, I think they prefer concrete, or up to 50 meters, they prefer concrete, or 50 to 90 meters. I mean, don't quote me on the numbers. I'm just giving you idea. So like there is one number up to which they prefer concrete, and between one number to another length, they are okay with both options, steel and concrete. And beyond a particular span, they say that like the guidelines say that concrete will not be economical, so go for steel. Yeah, and obviously the reason is that concrete is not good in tension, so you have to go for pre-stressing. Pre-stressing eventually makes it like at a point, if you go beyond a certain point, and the amount of pre-stressing steel you have to put in, the stresses that you introduce into concrete become very high because of pre-stressing stresses. Yeah.
So
Yes.
I am on doubt. So
Yeah.
so you already
Hello, sir.
said about steel.
What's your first name? Alvin Terry, Leo Alvin Terry.
Leo
What's your first?
Alcindor. Yes.
Leo Alvin Terry. That's your. So how should I call you? Is it Leo?
Leo,
Is it
Leo.
Alvin?
It's
Leo. Okay.
it's Leo, sir. Okay.
Okay.
So you already said about steel in elastic state 0.3 Poisson ratio and 0.5 in plastic state, and you already shown a graph showing that in one side 0.3 Poisson. Can you explain once more that point? I didn't get that.
Okay, let me try again. Unfortunately, my pen stopped working. So what I was saying here is that this is the elastic part. This is
Okay,
plastic
sir.
part in the stress strain plot, right? So this is, I cannot draw it here. So this is the strain and this is stress on the vertical axis.
Okay.
So this is elastic part, this is plastic part, let's say, and this is again unloading, which is also elastic part. The unloading
Okay.
is elastic. Whatever plastic strains you had, that gets accumulated, but
Okay.
unloading itself is elastic. So in this part and in this part, your Poisson's ratio for these deformations and these deformations, your Poisson's ratio should be 0.3. But for these
Okay.
deformations, your Poisson's ratio should be 0.5. So I mean, you usually don't use them for design. Because we design only mostly in the elastic part. We don't design in the plastic part. But this is good to know whenever you want to develop some advanced tool or something.
Okay, sir. Thank you.
Yeah.
Hello, sir.
Yeah. Who is this? Gajen? Is it
Yes,
Sayan?
sir.
What's your first
Yeah.
name?
Sir, my name is Shayan.
Sayan. Okay. Where are you from, Sayan? I mean, you are pronouncing it Sayan. So are you from Bengal
No,
or
I am
which?
from West Bengal. West Bengal.
West Bengal, right? Yeah. Otherwise, I would have pronounced it Sayan, but you are pronouncing it Sayan.
Yes.
Yeah. Okay, Sayan. Tell me.
Sir, my question is that in the PDF it is written gauge length equals to 5.65 a to the power 0.5. So what is that a there, sir?
A is the cross section of the coupon. So
Cross section, whole cross section.
one second. I'll tell you. So this is the coupon, right? So it has also third
Yes.
dimension. These are the two dimensions
Okay,
you can
okay.
see here. In the third dimension, it has some depth, some thickness. So if you cut the coupon here, right in the middle, if you cut it,
Okay,
there
sir.
will be cross-section area of that cut cross-section. That cross-section area is A0.
Yes. Okay, sir. Okay, sir. Okay, sir. Thank you.
All right, folks. So I think I'll conclude it today now. It's